Thanks for having me here and for this nice opportunity to be here again. So this is joint work with Florent Beniaish George. And the issue I want to discuss are eigenvectors. So we had mostly talks about eigenvalues so far. The model I want to consider is a model of matrices that can be written as actually well, T is a triangular matrix, not a diagonal matrix. So of course, the eigenvalues of our matrix are going to be the diagonal entries of T. And the particular, you can also usually write them as UDV, where D is diagonal. Those two representations are often helpful. But in fact, I want to deal with a special case of those which come from a model of matrix where the density over matrix element is just e to the minus n trace of V of m star dm. So it's proportional to that with a normalization constant. So particular cases, a particular case is V of x. V of x is x. This would be the V-short case. Okay, except that I'm not looking at x star, I'm looking at x itself. So V-short or Ginibri. So actually, maybe I should call it Ginibri, not. Okay, so I will always assume, that will be important throughout, that V of x squared minus alpha x squared over 2 is convex for some alpha. Okay. So the example I gave before, of course, satisfies that with alpha equal 2. Okay, and what I care about are the eigenvectors. So this matrix has eigenvalues lambda 1, or maybe I should call them T1. Are eigenvalues. And it has corresponding eigenvectors, which are VI, which I'll always take normalized such that V2 is 1. And the basic question I want to address is the inner product of VI, Vj. So now when I write that, you should realize there is already an issue of ordering of the eigenvectors. So the ordering of the eigenvalues, if you want. Vi is, of course, the eigenvector corresponding to Ti. So this is lambda, or to lambda I. This is lambda 1. This is lambda n. But unlike the Hermitian case, there's no natural ordering of the eigenvalues. And we have to choose one. And when we talk about Vi, we should say which eigenvalue are we talking about. And the ordering I'm going to look at is the following. We are going to take pick Zi points in C. Let me write already what I want to take. Usually, I will usually take Z1 to be Z, and Z2 to be Z prime. That's my usual choice, but what I'm saying works in general like that, okay? And now define lambda I such that the distance of lambda I to Zi is smaller than the distance of lambda j from Zi for all j larger than I. Okay, so lambda 1 is a point closest to Z1. Lambda 2 is a point closest to Z2, except if lambda 1 happened to be closest to Z2, then I disregard lambda 1 because I've already matched it, and so on. Okay? So it's successively matching the lambdas to a vector Z as written. In fact, we only care about the first two because we are going to look at, mostly we are going to look at just V1, V2, but this is this. Now, there are several notions of eigenvectors angles that one could look at. This is a natural one. This is not necessarily the most useful one or the most studied one. In fact, one can also, and for some differential equations, as we saw, this might be a good choice as well. One can also look at Ri, Rj star, Li, Lj star, where Ri are the right eigenvectors and L are the left eigenvectors. So for some applications, this notion is better. This notion has the advantage that it is invariant of scaling of each eigenvector, because then if you scale the ice eigenvector by a constant, the ice left eigenvector will be scaled. If you scale the right one by a constant, the left one will be scaled by 1 over a constant, and then this will be a natural thing to do as well. And in fact, this notion has received a lot of attention, mostly in the case in the Ginebra case, V of x equal x. And there's a long list of people who contributed. Crawford, Rosenthal is a recent work, and Bourgade and Dugas. Those are recent works. There's work of Novak with co-authors, with Tarnowski. All those are works from very recently. And then there are older works. There's Fyodorov has work on that. Burda and co-workers. And maybe the start of the story and the people who initiated and introduced this notion were Choker and Melling. So this is 98. Okay, so it has some history, but I'm not going to deal with that. Most of these works deal with a Gaussian case, which, as we will see, is a bit special. Okay, so now let me state a theorem. So suppose, so fix Z and Z prime in the way that we have just described, so just two numbers, and then choose the ordering that I wrote there. And then we have two eigenvalues, let's call them lambda and lambda prime. So lambda is the eigenvalue associated to Z and lambda prime. So typically, unless you choose Z, but if this is the support of the Ginebri law, maybe if this is Z and Z prime, lambda will be somehow very close to Z, and lambda prime will be very close to C prime. Okay? And we let V and V prime be as associated eigenvectors. And then I introduce another object, the random variable Y, which will be okay? Good. So this theorem, so that's a setup. And remember this assumption is important. And then there are two theorems. The first theorem is the following. The probability that y is larger than delta is smaller than 2 exponent of minus alpha over 2 delta. Okay, and this implies immediately that if n lambda minus lambda prime is much larger than 1, then v prime, which is square root y divided by square root n lambda minus lambda prime, goes to 0 at some explicit rate. Okay, because y is essentially bounded. Okay? So in particular, if you are separated much more than the typical distance between eigenvalues, which is 1 over square root n, the correlation goes to 0. Okay? And in a quantitative way. Sorry? Yeah, that's the distance, right? The typical distance between eigenvalues is 1 over square root n. Ah, there's a square missing. Thank you. Thank you. Yes. Okay, so that's theorem 1, and this is for any v. And then theorem 2 is the easier case, which is v of x equal x. And then fix z1 up to zk, satisfying square root n zi minus zj larger than n to the epsilon for all I not equal to j. So this means mesoscopically or macroscopically separated z. Okay, and this is or k is finite. And take theta I to be IID uniform of 0 to pi. Then the statement is that square root n lambda j minus lambda I e to the I theta I vi e to the I theta j vj. This inner product, this scaled inner product is this collection for I and j converge to IID standard complex. Gaussians. And actually, the y from theorem 1 is exponential 1. Okay? So this tail estimate is kind of precise. Okay, and in fact, my reason for giving this talk, the talk about this topic, is that there is a conjecture and an open problem that I would like to advertise. And so the conjecture is that this statement, true in setup of theorem 1. Okay? And you'll see why why one should suspect that. That's really what I would like to convince you, besides telling you some details of the proof. Now, I should add that this is backed by numerics. But unfortunately, we have not been able to settle this. This is backed by numeric and by a convincing heuristic that I will convey. Questions about the statements? So here it's this collection, yeah, this collection of random variable with I and j, of course, I not equal to j. So y is take any of them, yeah, sure. So which one? Okay. So the basis of argument and the proof is a change of variable formula. This should not really surprise you. So we are writing, so suppose that xn is distributed according to this law that I called P. Xn is my matrix. Okay, and we write xn to be un, tn, un star, where un is unitary and tn is triangular. Okay. And now, in order to make this unambiguous, at least as far as t is concerned, we're going to introduce the admissible set O. So O is a collection. This is it's a subset of C to the n. So O will be an ordering on the diagonal elements. Okay, the diagonal elements are complex, and the ordering is such that if I denote sigma O, so O is just T1 up to Tn, it's just this vector, and sigma O is just going to be T sigma 1 up to T sigma n, so it's, well, sigma is a permutation. And the set is admissible if sigma O are pairwise disjoint. And Cn minus the union of sigma O has zero Lebesgue measure. Okay? So it's those orderings which determine the order in an unambiguous way. Okay, so any other permutation. So it's easy to check that with the orderings that I have just defined, this will be the case unless you have certain equalities of distances, and it's easy to check that this equality of distances happen with Lebesgue measure 0. So the ordering that I have given in the theorem, or the ordering that I have described here, is an admissible ordering. Okay? And so this example is admissible. So this ordering is admissible. If you accept that the joint distribution of the lambdas is absolutely continuous with respect to Lebesgue, which it will be. Okay. So the main algebraic tool, which is kind of well known, maybe not in this exact formulation, there is no originality here, is the following. So suppose that we have a density rho of M, which is, so rho goes from Mn, space of matrices, to R plus, and rho of M is equal to rho of U, M, U star for any unitary. Okay, so in particular, the density I wrote in the beginning satisfies that, because it was a trace of MM star, and trace of MM star does not depend on U. Okay, then the map UT goes to UT U star, pushes Cn du to rho of M dm. Okay, so we have a representation in terms of T and U, chosen in a particular way, of the joint density of the matrix. Okay, is that clear? Is the statement clear? This is just a change of variable. At the end, it's just a change of variable formula. I didn't say what delta is, but delta of the vector T is just a product of Ti minus Tj for I less than j. If I'll have time, I'll say something about the proof of this statement, but as I said, it's pretty standard. Now, note the following, a particular case. This explains why the Ginibri case is easier. If you take V of x equal x, okay, then rho of t is just delta of Ti, of the, maybe I'll write it like that, delta of Tii squared times e to the minus n sum of Tii squared plus sum of Tij squared I less than j. Maybe twice. No, t is diagonal. That's okay. Okay? And the important thing is that these factors. So this becomes some function of Tii times some other function. So it is this dt times du. So this is rho of t. Sorry, it's this. And the point is that these factors to Tij for I less than j. So the diagonal elements are independent of the off-diagonal elements. Okay? Now, why is that? And in particular, and T12 square, so I forgot the n, I believe. Yes, there is an n here as well. And in particular, T12 is normal 0, 1 over n, or 2 over n, or something. Okay? So the law of T12 is very simple. Now, why is that relevant for the question that I was asking? So remember that M was U, T, U star. So suppose that I have an eigenvector V. So MV equal lambda V. Okay, this immediately, if you plug it in, it immediately tells you that T U star V is lambda U star V. Okay? That is, up to a rotation, the eigenvectors are exactly the eigenvectors of T. But T is triangular. So T is a matrix that looks like that. Sorry, let's write it like that. Sorry. It is lower triangular. So what is so this is lambda 1 and this is lambda n, according to my ordering. And what is the eigenvector corresponding to lambda 1? Well, it's just E1. Actually, it should be upper triangular. Sorry, upper triangular. Okay? So this times E1 is just lambda 1 E1. So E1 is an eigenvector corresponding to lambda 1. What about the eigenvector corresponding to lambda 2? Well, the eigenvector corresponding to lambda 2 is just a vector of the form AB. So V2 is AB. And all you have to do is to compute A and B. So if you do that, you discover that you get the equations at T11. Why don't I write explicitly the? So you get that B is minus A times T11 minus T22 divided by T12. Okay? And there is a normalization, of course, that B squared plus A squared is 1. Okay? But what is the inner product between these two vectors? Well, the inner product of E1 and this vector AB, E1 and this vector AB0, okay, this is just A, which we can read from that. So if we do that all together, we get that V1, V2 modulus is just equal to T12 divided by the square root of T12 square plus lambda minus lambda prime square. And if you define y to be n times T12 squared, this will be the y that appears later. Exactly this definition. Okay, so it's just a reverse of this map between the inner product and the lambda minus lambda prime and the T12. Okay? So now remember that in the Gaussian case, T12 was Gaussian. T12 itself. So, sorry, what I wrote here is nonsense. T12 is normal complex. Sorry. T12 is normal complex. The square is exponential. The modulus is exponential. The modulus square is exponential. Okay? So, so this immediately gives theorem 1, theorem 2. Okay, if you just do that for k in different ones, you will get the joint law of the t's, and it's easy to check that what happens. But certainly it gives theorem 2 for k equal 2, or just 2.
They are.
Sure they are. They are the eigenvectors that correspond to lambda 1. Right? That they satisfy this equation. The matrix times E1 is lambda 1. Okay? So that's exactly the point. They are the eigenvector corresponding to the ordering of the diagonal elements that I have chosen. Okay? Good. So we have that. And good. So now I want to, so as you see, this second theorem, in this context, it's much easier than the work that people have done involving both right and left eigenvectors. If you take a look at these papers, it's more complicated. But for the question I'm asking, it's actually trivial for the Gaussian. Okay? Now, let me give you the proof of theorem 1, and then I'll give you some evidence why the conjecture that I advertise should be true. So I've erased the theorem, unfortunately. Okay, so proof 1. So what do we want to, we want to prove that when you translate things, you really want to prove this. So the point is the following. Fix TII. Condition on TII. Then the law of Tij, remember, all we care about is T12. But the law of Tij conditioned on TII has a density which is proportional to e to the minus n trace of v of t star t. Okay? Now the map, because once you condition on TII, the delta terms are, the van der Monde term is given. Okay? But this means that the map between Tij to the trace, on the other hand, the trace of f of t star t, where f satisfies where f of x squared minus alpha, where f of x squared is convex, this map is convex. This is a consequence of what is known as Klein's lemma. And because of that, this means that the Tij satisfy log Sobolev inequality, and in particular, they give you the... Now, on the other hand, even conditioned on the TII, the mean of Tij is 0 by symmetry. That's easy to check. So the log Sobolev tells you that conditioned on the TII, they cannot fluctuate much. And that gives you the result. Okay? So, so this is convex. F of x squared minus alpha x squared over 2 is convex. So you apply LSI, log Sobolev inequality, and that gives you immediately so E of T12 equals 0 plus LSI gives you a conclusion. Okay, so that's pretty simple as well. So the results we have are simple. Now, why do I believe the conjecture? Good. You might wonder why there was a square root n, but the square root n is because f is multiplied by n in our expression, right? It was e to the n times a trace of. Okay. So let's take a simple case. Let's take v of x to be x plus x squared. And now we can start to compute what is v of t star. And when you do that, what we care about are the terms that depend on t12. Right? We want the marginal on t12. So what you'll get is something like that. You'll get t12 squared plus twice t12 squared. I hope I'm not making a mistake in computation. Then we'll have twice t12 squared times t22 plus t12 squared. And then you will get plus the same minus the same quantity with imaginary. So actually, yes. And so I'm having a, sorry. Is a trace of that, yes, thank you. Trace of that, plus negligible terms. So actually it's 1 over n trace, something like that. So plus negligible terms, plus plus negligible terms, plus terms independent of t12. Okay? That's what you get if you open the parentheses, and if I got the scaling right, which I now suspect I don't, but if you write the scaling correctly, then this is what you should get. Okay, now what do I mean by negligible? Negligible are terms that I can show by log Sobolev that they go to 0. I don't care about. Yeah, I guess that what is written here is not for the variables t, but for the normalized variable t, namely square root n times t. So I think this is what it should be. Okay, and this you can rewrite as t12 squared times some object that I will call capital X, plus real of t12 times real of some variable z, minus imaginary of t12 times the imaginary part of z. Where x and z are these variables that appear here. So z is, for example, this variable, right? This variable divided by square root n. Okay? Now, this variable, again by log Sobolev, can be shown to concentrate. So you expect this capital X to go to a constant. You have to be slightly careful because these variables don't have a priori mean 0. You have to show that somehow the conditional mean conditioned on the TII has not changed the mean. But that's plausible, so let's suppose this goes to a constant. So we're not worried about that. But these variables, at the best situation, are not going to a constant, because they have this 1 over square root n scaling. If you believe some kind of independence here, these variables should go to a Gaussian. This is a scaling, if you compute formally variances, this is exactly the scaling that should give that this is Gaussian. If that were true, so if we could show Z is really Gaussian, let's forget about imaginary and real. Let's treat everything as if it's real. It doesn't change anything. Then what we get is that the density of T12 conditioned on TII should be the expected. So it will be e to the T12 squared times a constant, okay, which comes from this part, basically. And here we will have e to the T12 times a random variable that I'm going to call z, which is a Gaussian. Okay? So if that were really Gaussian, what we will get, so you will have this expectation with respect to G, right? Conditioned on T12 and TII. This is really the computation I need to do if I want the marginal on T12. I just have to integrate over all the extra variables. So if this is really Gaussian, this will give me e to the minus some alpha, or not alpha, beta T12 squared, which is a Gaussian distribution, okay? Which is a claim. So everything boils down, so we started with asking about the distribution of one element in the decomposition, and we end up with a task of proving a CLT with for a combination of elements. Okay, is that clear? And that presumably should be easier. Unfortunately, this does not, nothing in this problem is exchangeable. The distribution of the Tij are different. There's nothing exchangeable. So if there is a CLT, it has to be done by some method that I don't see yet. Okay? So and as I say, numerics strongly support this. So the numerics strongly support the Gaussian distribution. So this is why this conjecture is true. Finally, well, I could, there is one thing that I didn't do, which is to tell you about this Jacobian computation, but okay, I have 5 minutes. I don't think I'll do it in 5 minutes. So maybe I'll stop here 5 minutes early. Oh, no, actually I have 10 minutes. Okay, then I'll do it. Okay, so, right. So this is proof of theorem 3 against sketch. So this is for those of you who have not seen such computations before. So you have UT, this you map by some map to UT U star. It's always better to work on Rn whenever possible than on manifolds. In particular, I don't like to work on U. So there's a map, so this is a step 1. We can make a map which goes from U n prime, I'll define in a second, to Rn n minus 1 over 2, where Un primes are unitary matrices with all non-zero entries and all principal minors non-zero. And one can show that this has a full Lebesgue measure. So we are not losing anything by restricting to that. And this map will simply give here 0, U12 over U11, U1n over U11, and here it will be, etc. Okay? So I hope it's clear. It's just normalizing, using the fact that this is really the number of variables. So this is an easy map that doesn't lose anything. Now, the other step, which I'm not describing, is that if you take U in U prime and T in, I'll call it TO, so what is TO? Those are matrices, those are triangular matrices where the diagonal entries are ordered according to my order O and not equal and distinct. Okay, so this, if you take that, then U star has full measure. This you do by showing that the condition that things are identical disappears. Sorry? As full measure over, it defines a matrix M, and it has full Lebesgue measure. So the restriction to TO does not reduce the total mass. Okay? This is what I meant. Okay, so now we have, so after we do these two steps, we have to, so we are in a good shape because all we have to do is to compute Jacobians. Because everything here is now a bijection, so this is not only a full mass, but it's actually a bijection. So now we have a bijection from this set plus this TO to our matrices, and we have to just compute the Jacobian. Okay. Now, maybe I'll do one computation. So we really, when we compute the Jacobian, because this is something that involves only U, and we don't care about factors involving U, at the end, what we need, we can go back to our original writing, take the maps that take UT, U star. So all these preparatory steps were just to say that we really need to understand this map, because we're really composing this map with that map, with the inverse of sigma. Okay? So we need to understand the Jacobian of this map. And for this, where U is in UN, right? So the first two steps told us that all the ambiguities are resolved by applying later the inverse of sigma. Okay. Okay. So now, what is a tangent space of UN at U? Well, those are exactly the collection of matrices UM, where M is in what we call IH naught, so those are the matrices that satisfy that M star is minus M, and MII is 0. Okay, it's anti-Hermitian matrices. Okay, so now we can compute the derivative, df of Tu at a point RH. So H is in the tangent space. This is in the tangent space of UN at U, and R is an upper triangular matrix. And if you compute that, you end up with, after some algebra, and using that the tangent space satisfies that, you end up with U star H, T minus T U star H, U star, yes, U star times, yeah, like that. So, but you know that U star H for H from here is exactly it's exactly this matrix M. Okay? Because the tangent space is U times M, and here I multiplied by U star. And of course, the outside U does not change the Jacobian, so I can forget about it. Okay, so what we need to do is to look at the map, at the determinant of this map, kt minus tk plus r goes to M. And k is in IH naught, and t is in Tn. That's our situation. Now, this space is decomposed to two. You can look at this matrix as upper triangular matrices plus lower triangular matrices, like that. And if you write the derivatives, you write the Jacobian, so this is with respect to k, this is with respect to r, what you get is you get here an identity, but here, because r is triangular, you get 0. Right? So you actually don't care what is written here when you compute the Jacobian. You only care about this part, which means that you only care about the lower triangular part here. Okay? And when you look at the lower triangular part, the claim, you can write what is, so for the lower triangular part, of course, R is not playing a role. Okay, so we are really reducing attention to looking at V equal KT minus TK, lower triangular. I hope this is clear what I mean. Okay, I'm looking at the lower triangular part of this matrix. And the claim, where T is given, and the claim is that this has Jacobian which is a product of Tii minus Tjj squared. And the reason is that if you write Vij from this matrix, you write it as Kij. So this is a map, I hope it's clear what Jacobian I'm talking about. It's a Jacobian from the entries of K, which are only upper triangular. K is not upper triangular, but the independent entries are only in the upper triangular part. T is given, and V is a lower triangular part. So the number of variables is correct. And what you get is something like that, Tjj minus Tii, plus the sum from k equal 1 up to j minus 1, Kik Tkj, minus the sum from k equal I plus 1 up to n, Tik Kkj. And what you discover is that if you choose the ordering correctly of the variables, what you get is a lower triangular matrix. So this matrix is, when you take the derivatives with respect to k, this will be a lower triangular matrix. So you have 0 here. And therefore, you only care about the terms on the diagonal, but the terms on the diagonal are coming from here. And since everything is complex, it's just going to be this difference square. So that's it. Good. Thank you.